Okay, so this is going to be, I'm going to do the quizzes that I gave the honors classes. I don't remember which section got which. I think this one is the one for slot 4. So, we just put like a 4 up here if we wanted to. It's not really that important. We're going to look at this particular circuit, and then I'll solve the one for slot 6 or whatever the other slot is. Okay, so the first thing that I like to do is I like to think about the voltages in these things. So the first thing we're going to do is we're going to start highlighting things. By the way, excuse the noise in the background. Mr. Keen is doing his, what do they call those things? Oh, his mousetrap cars at the moment. So there will be some cheering and hopefully cheering and no booing. Anyway, so I'm going to start highlighting things. So we know that all this area over here, right, all of this has a particular voltage. Okay, so we're going to go ahead. Everything I can touch by a wire has the exact same voltage. So all of this that is in red has a certain voltage, right? Okay, we could say everything in blue down here has its own voltage. Okay, that is the negative side of the battery. And so this particular diagram doesn't have a ground, but if you don't have a ground, I always recommend the negative side of the battery gets to be voltage 0. So all this blue business is going to have a voltage of 0. Okay. Now, in between red and blue, it should be orange, but I don't have orange. So, or I guess it should be purple, but I'll just do green in between. So everything in here has a voltage of whatever this green voltage is. Now, we don't know what that is exactly because we can't tell, right? It's not so easy. Okay, so let's go ahead and label these suckers. Okay, so for the blue areas, we'll go ahead and say that this is V0, and we're going to call that 0. Okay, why? Because it's on the negative side of the battery. There isn't a ground over there, but by making the negative side of the battery 0, it means that everything has a positive voltage, okay? So the battery is delta V equals 24. So that means everything over here is 24 higher than the other side of the battery. So we'll call that V1 is 24 volts. Okay, now the green, we don't know what that is, but if we wanted it, we would call that so it would be V2, and we don't know exactly what that is. Okay, cool. Now, what we're doing, once we've done that, the whole rationale for all of that is that we really want to get at, I'm going to use a slightly thicker marker here. What we want to get at is we want to get at what's in parallel and what's in series, right? And so as far as what's in parallel, we're looking for things that are going from the same voltage to the same voltage, right? So hopefully you'll note that this one's going from red to green, and this one's going from red to green. So because the voltage differences are the same, those two are in parallel. So R1 and R2 are in parallel, okay? And then we'll note that this one's going from green to blue, and this one's going from green to blue. So we will say that R3 and R4 are also in parallel, okay? All right, so that's very helpful. Now we have to think, are any in series? So we're looking for one where all of the current that flows into one also flows into the other. I don't see anything that looks like that. But just because we're here, I'll just go ahead and say that whatever leaves the battery here, that's going to be I naught. Okay, it will remain I naught until it hits a junction, right? So all of that is I0. Okay, whatever leaves the battery is also what's going to come back into the battery. So all of this is also going to be I0. Okay? Now we will note that I0, when it hits the junction, it's going to split. It's going to go this way. And since it's going through resistor 1, I'm going to call that I1. And then this, because it's going through resistor 2, I'm going to call that I2. Okay? Note that I0 equals I1 plus I2 because everything that flows in has to flow out. Okay, when these two recombine, I'm going to get I0 again for just a little bit because they're going to recombine to get I0 again. And then it's going to split here, and it's going to go this way. Okay, and it's going to go this way, the two halves of it. It won't be even halves, but they will split. And this will be I3, 3, and this will be I4. Okay, cool. All right, so I think we're in pretty good shape now. Okay, so that's essentially what we're looking for, right? So we're going to be looking for the voltage drops on the resistors. So we're going to look for the voltage drops and the currents here, 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 and here, okay? Okay, so the first thing we need to do is usually I want to start like simplifying this until I can get something that makes sense. Okay, so first thing, I'm going to pause for a second while I redraw this sucker. Okay, so I have redrawn it. And what I've done is I've replaced R2 and R1 with R12 and R3 and R4 with R34. Okay, note they were in parallel, so R12 is going to be, let's see, so that's going to be 1 over 100, so that's R1, plus 1 over 250, that's R2, okay, raised to the -1 power. And I believe if we do this right, which is really the only way to do this, we're going to get 71.425 ohms. Okay, which is an annoying number, but you know, what do you do? Let's deal with it, right? Okay, and then R34 is going to be 1 over R3, which is 350. Again, remember we're using this formula because these are in parallel. Okay, 1 over 200 ohms. Okay, we'll raise that to the -1, and we'll get 127.27 ohms. Okay, what we like about this, one of the things, the pigs thing that we wanted, you know, we're always worried about pigs. This number, 71, has to be lower than either of those two, and it is. 127 has to be lower than both of those, and it is. So from a pig standpoint, we're feeling pretty good about ourselves. All right, now from a voltage standpoint, right, we must note that we've eliminated no voltages here by going from these to those, right? And so we still have this, oh, that's the wrong color. We still have this right in here as being green, right? So we still have what we would call, this would be V2 still exists in here. This is a horrible color. It's very hard to see. We'll use a darker green the next time green comes up. Okay, for the red, you know, up here, we still have V1 equals 24 volts. Okay, so let's go ahead and highlight that. Okay, so all of this is red. Okay, and then at the bottom, all of this still has a voltage of 0. So this is still V. V0 equals 0. Okay, so right, and this handwriting is awful, so let's kind of clean that up. 24 volts. Okay. All right, so this is now what we would call a simple circuit. So we know that we've got I0 going all the way around this, right? Okay, cool. So let's just keep going. We're going to keep going, and let's see. Now we've got 24 volts is right here. 24 volts, that's the battery. Okay, I'll actually do this live because this isn't really all that complicated. All right, so there you go. Okay, I'm now going to combine R12 and R34, so I'm going to get REQ. And how do I get that? I'm going to add up these two values right here because this is in series, right? So I'll get 71.425 ohms plus 127.27 ohms. So if I add all of that up, I think it's a 198 what do I do? I can follow my work, I just can't find it. 70 ohms, okay? So there's my REQ. I know the voltage of the battery. I'm not really that concerned about this being V0 equals 0. There's no reason not to put it on there. So I will go ahead and put it on there. This will be V1 equals 24 volts. Okay, I'm just kind of like getting at what it is that we still know, right? So this is still red, okay? And this is still blue, right? Everything I can touch with a battery, okay? So in other words, I know if I want to get the current leaving the battery, oh, that's the wrong marker. Nope, that's just wrong. Did I gum it? Okay, let's see if we can get a better eraser. Oh no, let's undo that. Okay, let me get this little eraser. Can we get it to be a little bit more gentle? There you go. Okay, anyway, so we know that I0 is going this way, right? Okay, so for one I0, we've got delta V, we've got REQ, so current equals delta V over R. Okay, always. In this case, we got battery, REQ, and this is the current leaving the battery. Okay, so I0 equals the change in voltage, which is 24 volts, divided by 198.70. ohms. So this is really annoying because we're going to have this really small number. I find that really obnoxious, but you know, I didn't create this problem. I just assigned it. Okay, that's my cop-out right there, right? Okay, so now I got I0, okay? So what I've been doing as I've been working these is I kind of start working back up, right? So I'm going to go back up to this one, and now I know I0, right? And I'm going to use that to kind of work on this one, and then I'm going to take that information and I'm going to use it to go back up here, okay? So let's start here. Okay, I know I0. So if I know I0 and I know R12 and I know R34, I can get the change in voltages across those resistors. So delta V12 equals I12, which happens to be I0, times R12. So delta V12 equals what's I0? Oh, yeah, it's that annoying number. Okay, I didn't quite give myself enough space, so maybe if I zoom in a little bit. So 0.12078 amps times R12, which is 71.429 ohms. So delta V12 is going to be 8.286271 volts. Of course, you guys know me well enough to know that I use entirely too many sig figs, right? Okay, so that's delta V12, so that's going from red to green, okay? Now let's go ahead and do from green to blue, or delta VR3. Delta V34. Okay, delta V34 equals I34R34. Delta V34, let's see, I34, it's the same, 0.12078 amps. Okay, if you wonder about that, notice that whatever current leaves keeps coming around, has to go through both, right? So it's the same for both. However, they have different resistances, and like an idiot, I have kind of crowded myself in here a little bit. For some reason, it's using a giant dot for that. Is there a way to change that? Oh, there is a way to change that. Okay. All right. Anyway, so we're back to black. Okay, so that's going to be amps. And then R34 is this annoying number, 127.27 ohms. Okay, so delta V34, if we multiply that out, we get 15.372 volts. Okay. So if we look at this picture, and this should be clean enough to see, I'm starting at 24 volts, and I'm going down to 0, right? V0 equals 0. So that means I'm going to drop some as I go here, and then I'm going to drop some more right here, right? Which means those two total drops should add up to 24 volts, okay? Do these two add up to 24 volts? Okay, and that's the question. That's a good test right there. It doesn't look like I did it, but I think it should be pretty clear that 8.62 and 15.4 do in fact add up more or less exactly to 24 volts, okay? So delta V tote needs to be equal to 24 volts, okay? And I think we checked that box, okay? Now, I think what's really cool about this, and what's really nice, is that delta V34, okay, notice that's going from green to blue, okay? And so if I look up here, I know the delta V4, because it's going from green to blue, and I know the delta V3, because it's going from, green to blue. So I know that delta V, and I know that delta V. Okay, now delta V12, okay, it's going from red to green, okay, which means I know delta V1, and I know delta V2, right? Okay, so I know all my delta V's at this point, which is sweet, okay? So now I just need to get the currents, right? So if I know delta V's and I want current, well, how do I do that? Well, delta V equals IR, so I equals delta V on R, okay? So we're going to do that 4 times, which is a little bit time-consuming here. Notice we have the resistances, okay? And I know the delta V's because I got them in the last step, right? Okay, so I'm not going to talk my way through that. I'll just put them all up here. Okay, we'll pause here. We're going to look at I1 and I2. Okay, so I1 is right here, and I2 is right here. Note we know they have to add up to I0. Okay, so if I take these two that I just solved for, okay, do these add up to, if I add them up, I get 0.1207 amps, okay, which is in fact I0. What was I0 is down here somewhere. Okay, notice that's the number we got down there, so we feel pretty good about that. I mean, within, rounding error, okay. Note that both of these have the same voltage drop across them, okay, that which we solved for earlier, which is this 8.72 whatever, right? And they just have different resistances. So this one is a resistance of 100, and this one has a resistance of 250. Okay, so we have those on the bottoms of these fractions, right? Okay, and then, okay, the other thing to note, if we had done some partitioning trick, which you certainly can do if you know how to do it, it's a little bit weird with 100 and 250. Those are kind of big numbers. But we should notice that we should expect 2.5 times as much to go this way as that way. And if you multiply this by 2.5, you get this within, rounding error, okay? So these are the pigs things, the things that sanity checks, make sure that you're kind of doing this the way that makes sense to you, right? Or that makes sense so that you're not just doing crazy stuff. Okay, sorry, I didn't mean to erase that. This will be, it sounds like they got a good car going there. Let's hope so. Okay, so we're gonna do the exact same procedure for here to here. We know this delta V, we know this delta V, they're the same. Okay, that's delta V 3, 4. So what's delta V 3, 4 is right there. We're gonna use it for both of them. We're just gonna use a different resistance for either one, right? So I'll go ahead and pause as I do the math. Okay, so here we go. So they have the exact same delta V, but they've got different resistances, okay? If I do the math here, I get I3 and I4. We should note one check on that, as we expect I3 and I4, because they're both leaving this junction, to equal I0, which is coming into that junction. So we can add these up and see what they add up to, expecting them to add up to I0. And I3 plus I4 adds up, and we get 0.1208 amps, which, pretty darn good, right? We feel pretty good about that. We should also note that because this has a lower resistance, we expect more current to go that way. Well, how much more? Well, this one's a little bit weirder, but we expect this one to be 350 times 2 over 200ths as big, right? So as a fraction, we can reduce that, and we'll get like 1 1/4, 1.75. So if I take 1.75 and I multiply that times, oh, dadgummit, sorry. This one's gonna get more, right? This one gets more. So if I take this one and multiply by 1.75, I should get that one. Let's see what happens. Okay, and if I do that, I get 0.0768. Okay, pretty darn close. Okay, like good enough for government work, as they say. Okay, so there you go. So here are our currents through all 4 resistors, right? And then let's see the voltages, the difference. So this is the delta V for, this is delta V1 equals delta V2 equals this. And this one is delta V3 equals delta V4 equals that one. Okay, so those are all your answers. All right, so that's the first one. Where's the second one? Oh, I put it on a different page. Never tried doing that. Let's just go ahead and save this. We'll call this combo circuit section 4. All right, hope this has helped.